one of my favorites. I mean, I know you're not supposed to have favorites among the components, but it's one of my faves. So let's talk about MOSFETs. MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. So thank God we came up with an easier way to say that. It's a two-port, nonlinear circuit element that lies at the heart of digital electronics. On a single microprocessor, there can be millions of these transistors on them. They're the dominant type of transistor, which is a class of elements that includes the bipolar junction transistor, BJT. And that is another important circuit element, but we do not have time to get into that one in detail. Maybe one day. I actually didn't used to get into MOSFETs very deeply, but I did talk more about BJTs. But MOSFETs are more useful for us as mechanical engineers, and so I decided to switch over and just talk about MOSFETs, prioritize that. So it's a brand spanking new lecture, hot off the press, a la 4 a.m. So MOSFETs are not just common to integrated circuits made of silicon, so that's the microprocessor. They're also available as discrete elements, which is the form most often encountered by the mechatronicist, which, to my knowledge, is the first use of that term, and I think it's pretty awesome, so I'm using it now. It's a thing. We are mechatronicists in training. So, what I mean by discrete element is one that you could, for instance, put on a circuit board or put in a breadboard, something like that, as opposed to something that's really, really, really tiny, that's part of a silicon semiconductor material. So there are two primary types of MOSFETs, the N channel and the P channel, determined by the type of semiconductor doping, negative or positive, N for negative, P for positive, used in the manufacturing process. These types are opposites, so we choose to focus on the N channel here. So we're just going to do N channel MOSFETs. P channel MOSFETs work like the same but reverse. So if you understand the N channel, you can understand the P channel. You just have to like flip-flop the wires, essentially. This terminology of doping of semiconductors, any familiarity with that notion? So it's like not many people are familiar with it. So a semiconductor, like silicon, does not conduct electricity well. But if you dope it through different processes, it becomes a good conductor. And if you dope it such that the charge carrier is an electron, which is negatively charged, then it's an N-type semiconductor. If you dope it such that the holes where there are no electrons, which are positively charged, are the charge carrier, then they're P-type. So we're going to consider the N-type here, the ones that are made from N-type or negative doping of the semiconductor. That's just like a little gloss on how they actually work. There's a lot involved in how they work. We're going to consider them just from the outside input-output properties, just like we've done with virtually all of our electronic circuit elements so far. We've said, well, they're made somehow and they behave like this, and that's what we're going to focus on. Okay, so in figure 4.7, so figure here, we see the circuit diagram symbol for the MOSFET. So I've labeled a few things on it to give us a start. So there are 3 terminals typically drawn in the configuration, or in the circuit diagram symbol. This terminal is called the gate. The G is the gate terminal. D is the drain terminal, and S is the source terminal. The current flowing from one terminal to another is labeled with consecutive subscripts. For instance, the current flowing from the drain to the source is IDS. Okay, so the current flowing from drain to source. And in fact, that is the direction that current flows through a MOSFET. It either flows like that or it doesn't flow. Is really what it comes down to. And you might think, what the hell is up with this terminology? Current flows from drain to source? That sounds backwards. And the reason that it's named like this is just a historical hiccup based on the fact that in an N-type, an N-channel MOSFET, we have electrons as the charge carriers, and electrons flow in the opposite direction of charge, that we consider to be charged. So if we think of it as being the electron flow and so the negative charge flow, then it works, but that's not how we think of charge flow, so it's kind of opposite. So just think it's backwards, and you're fine.
Can we fix that, like, in terms of how everybody views current? Should we just, like, switch it
Should
to
we?
the correct direction?
I mean, it's sort of like the question, should we move over to all SI units in the United States? Yes is the answer, but no is the other answer that keeps emerging. It's because we are, it causes a lot of confusion. And actually, I think this would cause even more confusion if we suddenly were like, electron flow is current. Then
Like a couple of generations, then it'd be like fixed and easier for everybody.
Yeah. Well, fortunately, it's above our pay grade. It's above my pay grade. Perhaps you will achieve a pay grade where you can actually do it. I mean, I could create this environment where we talk about charges being the flow of electrons, and then like if you guys ever looked at any source outside of this class, then everything would be backwards. So I'm not going to do that. But you know, it'd be fun. We are using this term mechatronicist, which is cool. All right. So another notation thing. Voltage drop across 2 terminals is labeled with concurrent subscripts. For instance, the voltage drop from gate to source, so the voltage from G to S, is V sub GS. It's a common notation, but we haven't used that in this class so far. Okay, the input-output characteristics of the MOSFET are quite complex, but we may, in the first approximation, consider it to be like a switch. In this model, called the S model for switch model, if the gate voltage VGS is less than the threshold voltage VT, which is typically around 0.7 volts, can range up to 1 volt approximately, the drain and source terminals are disconnected or open from each other, and so we are operating in off mode. So if the voltage, if the gate voltage, it's called gate for a reason, it's very suggestive. So if the gate's low, then it's not flowing current from D to S because it's an open circuit, right? Or it's effectively an open circuit. But when we raise the gate voltage above a certain threshold, the threshold voltage, then D and S are connected via a short, and current IDS can flow. So that would be on mode, and current would flow like that. So it's a lot like a switch, right? So if you think of the switch in the room we walk into, turn on the light bulb, we throw the switch and we connect the circuit up, and then when we leave, we flip the switch down and it disconnects the circuit so current doesn't flow. Just like that, but we control it with a voltage at the gate. Okay? So that's cool. And if a MOSFET just behaved like that, it wouldn't be very complicated at all. But it is a little more complicated than that. But not a lot. We can actually, it gives us some good intuition. So the actual input-output characteristics of a MOSFET are much more complex than the S model captures. The S model can give us intuition and suffice for digital logic circuit analysis. So if we just care about high-low voltages, so digital circuits, we don't really do a lot with them in this class, but they are just concerned with a state being, a voltage level being either above a threshold, so it's on, or below a threshold, so it's off. So it's interpreted as on or off. So the actual value isn't important, it's just that it's above a certain amount or below a certain amount. TTL is the most common digital protocol for logic, and so it's 5 volts is on, 0 volts is off, and there's actually like a threshold value in between that switches from one to the other. So if we just care about that, we can actually use this sort of model for a MOSFET and think of it like that. We can build some logic circuits that are pretty cool, like or and gates and stuff like that. But we aren't going to get into those. They're really cool, but we just have one semester, so we just can't do all of it. However, we are concerned with analog circuit models mostly as mechatronicists. Specifically, we use MOSFETs to drive power-hungry loads like motors, okay? Need a lot of power. With high-power sources controlled by low-power microcontrollers, okay? So that's like kind of big picture what we're going for here. This is why we're talking about MOSFETs. MOSFETs can be used for lots of things, including amplifiers and all kinds of good stuff. But, and clearly microprocessors and all that. But what we're going to use the MOSFET for is to say, okay, we have this load, like a motor that requires a lot of power. We buy a power source, it puts out, some constant voltage, like it's say like a 20 volt power supply, and it can provide decent amount of current, so it can drive a motor, for instance, or some other load that requires quite a bit of power. But we want to vary how much voltage is delivered to the motor so that, say, like the speed can be varied, for instance, if it's a motor. Or if we're driving a different type of load, whatever it is that we're driving can get different power levels to it. So we want to control that. We don't want it just to be all the way on, and then sometimes, all the way on or all the way off, but you still need to switch to make all the way on or all the way off. So, yeah.
So, not to get off task, but I heard there's going to be like a small electric motors next semester. Will you be dealing with this? Like in electric motors?
So, I think that Washko is teaching an electromechanical machines course. I don't know what he's covering in it. I think it's a pretty new course, so I'm not totally sure what he's covering in it. I'm teaching an embedded computing course, which is going to use motors as one aspect of it. So we're gonna program microcontrollers to control motors, essentially. And that's, yeah, so it is going to come into it. We aren't going to use MOSFETs in that application. We're going to use some other types of components, but yeah, it's something you could use as a MOSFET. and I actually used to teach just BJTs pretty minimally in this class, and then I ignored MOSFETs. But then last year it occurred to me when we were doing some student projects that really the MOSFET is more important for us to know how to use. And so I decided we would switch and focus on the MOSFET instead. A little easier to use to do things like driving the motor. So I think it from a microcontroller. So yeah, really useful things. So you can there's another device that we're going to talk about on Monday called the operational amplifier, op-amp. Can also be used to drive motors with. But this is like the easiest component to do it. Like, quick and dirty and cheap. Especially if you're just gonna like turn on and off like a fan or something. This is definitely the way to go. Yeah, so this is like a really nice little, and we're gonna do in the example today a circuit that you could drive a load with, just like a MOSFET. Just pop it in there, and then you can control a bigger supply. So yeah, it's super useful, the MOSFET. And then our microcontrollers allow us to do things like put out an analog voltage at any level we want. But the thing that sucks about a microcontroller is that it can't output very much power. So let's say it's got like, it might have like 3 or 5 or 10 analog outputs, but they can't supply very much current. So they can supply voltage in a range like 0 to 5 or 0 to 10 volts, but the current draw can't be very large, otherwise it can't supply the power. So what you do is you use the power capacity of like your just straight up DC power supply, say, that's not variable, and you use the variability of your microcontroller voltage output, and use a MOSFET to sort of control the big power supply with the microcontroller. So it's kind of the idea of what we're doing here. So we need to turn now to a general model for the MOSFET, after which we consider the method of analyzing MOSFET circuits, and we'll do that through an example. This model is actually pretty accurate. It's called the switch unified model. The thing that sucks about it is it's very nonlinear, and so it therefore causes headaches for us during analysis, because nonlinearities coming in create nonlinear equations. It's also not just nonlinear, it's piecewise nonlinear. So it's like not even a continuous nonlinear function, which would be better, but it's not even a continuous, or it is continuous, but it's not even defined without a piecewise function. So that's also frustrating. As usual, we're concerned with the element's voltage-current relationships. So we'll investigate them, and this is the definition of the switch unified model. So let K be a constant parameter of the MOSFET with units amps per square volt. K can be found from parameters of a given MOSFET. So you can find K from the like the spec sheet for a given MOSFET. The current into the gate is 0. Okay, so we're saying that the current coming in here in the gate is 0. This is just like universally true of MOSFETs. It essentially has like infinite input impedance. It doesn't really draw any current. We can approximate it at least as being 0. It doesn't draw any current into G, which is good because that means that this gate voltage we can change easily. We don't have to worry about it sucking a bunch of current and changing our voltage. So we can just control that independently. The current from drain to source, which is kind of like our output in a sense, the current from drain to source is controlled by the two voltage variables VGS and VDS. So we essentially control this current that flows from D to S by this voltage, the gate voltage, and this voltage, the drain to source voltage. Those are the two variables that affect how much current's flowing through. So let's look at the different possibilities. So it's piecewise. The first possibility is that if the gate voltage is less than the threshold voltage, it's not going to flow any current. So if the gate voltage doesn't reach the threshold voltage, just as in the switch model, right, it's like off, right? It's off. It's not flowing any current. Okay, so that's the first thing. It behaves like the switch in the cutoff or in the off state, which is nice. So that part of the switch model is totally correct. It's the same. It's the on state that gets us our complexity. So there are two possibilities for the on state. The first one, this is parenthesis. The first one is that it depends on both VGS and VDS. Okay, so it depends on both voltages. And this one applies when we've got a gate voltage above the threshold, so it's on, right? But our drain to source voltage is less than this difference between the gate to source minus the threshold. So it's when VDS, this voltage here, isn't high enough. So this one's high enough, but this one's not what we're going to call high enough to be in our preferred mode, which is called saturation, the next one. So this one is this intermediate stage here. This one's is very nonlinear, right? It's nonlinear. It varies in two variables too. It's VGS and VDS, so it's not very nice to work with. So, okay, we call this we still call the cutoff or off. This intermediate one we call the triode region, and we don't like that region. We don't like it. We don't want to be there. If we're there, we have all this nonlinearity happening, and it's hard to work with. And then in this last situation, we have the gate source voltage greater than the threshold, so it's on, right? But we also have this drain source voltage, so this voltage is above the GS, so the gate voltage minus the threshold. So it's like it's in this higher region of voltage, and this is called the saturation region. So we want to live here and here, and we don't want to live here because it's more complicated. And in fact, we can, as we'll see in the example, we can avoid that region if we're careful. So that's our goal, is to avoid it. In most applications, there are some when you need to use it. Okay, so that's what this paragraph is describing. But notice that in saturation, the nice thing about it is that we don't have VDS in it anymore. It's still nonlinear, but we have VGS, which is the gate voltage that we're going to control, right? That gate voltage. It doesn't draw any current. And then VT, just that threshold voltage of like 0.7 volts or whatever. So that's a really nice expression. I mean, it's nonlinear in VGS, but otherwise it's pretty nice to work with. So we want to be in saturation or cutoff, and notice that this behaves like a current source that's controlled by VGS when we're in the saturation region, because it doesn't depend on the voltage across it. So remember, the definition of a current source is that the current is specified, and then the voltage is whatever it needs to be to make the current what it is, right? So we specify the current, and then the voltage has to be whatever it happens to be to make that happen. This is that because it doesn't depend on voltage at all. It supplies a certain current regardless of what the voltage is across it. That's nice. So that's a current source, but it's controlled by, so this is kind of new, because most of our current sources so far, we have just said come from outside of the circuit, right? It's just some function, it's given, right? It's like either some constant value or it's a sinusoid or whatever it is. It comes from outside the circuit. But this one depends on something inside the circuit. And so a source controlled by a variable in the circuit is called a dependent source. This behavior as a dependent current source, it can also be turned off. So it can be turned off by going into the cutoff region, or it can act as a dependent current source, is the most valuable for us. And that's where we want to be. We want to have this thing act like a dependent current source or be off. And that's our goal in these designs. So the switch current source model, so we started with just the switch model, the S model, right? Really simple. It kind of got us most of the way there, off and on, but it didn't describe on very thoroughly. So then we introduced this switch unified model, which is actually pretty accurate, but it's really nonlinear, kind of annoying. The switch current source model is the one that you're going to see most people use out there, like on the internet or in textbooks and whatnot. And so I wanted to mention it. So it's actually just a recognition of this behavior of an elimination of the triode region from consideration. So we're just going to ignore the triode region, and we're going to treat this thing as a dependent current source that can be turned on and off. And that's what the switch current source model does. It's a reasonable assumption if we can guarantee operation in cutoff or saturation only, and that we're never going to go into triode, or if we do, it doesn't matter what happens. Okay, and that brings us to our example. Oh man, I didn't make the name right. What should we call it? MOSFET period, because I'm not creative right now, I'm too tired. So we have this circuit shown here. Look at that, we've got ourselves a little MOSFET in there. I know, surprising, right? And it has a load that we're going to try to drive voltage across and current through from this what we could call our power supply or a power source. Okay? We want to control how much that source delivers to this load with this, what we could call our signal source. Signal has this connotation that it can't provide a lot of power. You can change it easily, but you can't deliver a lot of power with it. So we have two sources. One of them is like, you can think is coming from like a microcontroller, like this signal source coming from the microcontroller. It can't really supply much power, but as it's connected here, this current is zero, right? This gate current is zero, so it doesn't have to supply power, which is nice. But it's going to be controlling this power source, which can supply the power. So that's what we're doing, and we're going to drive it through a resistive load. I gave the resistance of the load, and I gave the K value for the MOSFET and the threshold voltage, and then I said this is a 10 volt power supply, so this is 10 volts. And I want us to solve for what the voltage across the load resistor will be, given a range of VG that is that keeps this MOSFET in saturation the whole time. So we're just going to say, what is VRL for various values of VG as long as we're in saturation mode? So over the whole thing. So that's the problem. And this is like really, I mean, we could apply this circuit like immediately, okay? So we could walk into the lab and apply this circuit. A resistive load, so a motor doesn't act as just a resistive load, as we'll discover. It's an inductive load, which is a little bit more complicated, but all you really need to do is add a diode in there and you're fine. So we can use this for a motor load, but this isn't a motor load because it's not inductive. It's just resistive. So for instance, you could be controlling a heater. If you had a resistive heater, so thinking as mechanical engineers, we're like trying to heat something, keep it at maybe some like controlled temperature, say. And we want to vary how much heat we're putting in through this heating element. This would be a way to vary that heat delivered through the heating element. So that's like one possibility. The load could be a heating element or something, or it could be a like a light source that's resistive light source, or all kinds of things. So here we go. Let's so we know that during saturation, the current from drain to source, IDS, has to be equal to K over 2 VGS minus VT squared. So that is just straight out of our switch unified model for the saturation region. We just copied that formula over. Bam. Okay, so we've got that. What we want to know is what the voltage across the load is going to be when this is true. Okay. So in this formula, so VT is a given, right? It's just 0.7 volts. So VGS is the thing that we don't know in this expression, but we actually do know it. So we know that VGS is equal to what in this circuit? What is VGS? In terms of sources and, in terms of our sources, what is it?
VG.
It's just VG, right? Yeah. It's just VG. And that's, we want VG as part of our solution, right? We want to know how the voltage across the load resistor varies when we vary VG, so that's good. So we have what the current is through IDS, or through the MOSFET, when we're in saturation, in terms of the variable we want to know our answer in terms of. So we're doing all right so far. That's a good start. The voltage across the resistor across the load is, from Ohm's law, VRL equals IRL times RL. we want to know what that voltage is, right? Voltage across the load is what we're solving for. So we need to write the right-hand side of that equation in terms of things that we know, which are what the sources are, right? We know what the sources are. We know what the threshold voltage is, and that's about it. So we need to write this. So RL is just a parameter. IRL is the variable we need to eliminate and write in terms of things that we know. So how are we going to write IRL in terms of things that we know? KCL, yeah, exactly. So from KCL, we can just look at this node right here, right? And we can say, oh, IRL, the current going into that node, has to equal IDS, which is the current flowing through the MOSFET. So we can say IRL equals IDS. And now we can rewrite the voltage across the load as being IDS times RL, which we solved for IDS already, right? We already got it. So let's plug it in. So K over 2, and then VGS we said was just VG, right? VG minus VT squared times RL from the Ohm's law back up there, or from this previous step. Good. So this is our load voltage. So in a sense, we're done, right? Like we've solved for the load voltage in terms of things that we know, including the signal source voltage here, VG. So we could plot it already. Like we could plot for different values of VG. The only issue is that we don't know the range of VG for which we're in saturation, right? So we're using this formula for saturation, and we say it's valid when we're in saturation, but we don't know what values of VG will leave us in saturation. So that's the last thing we need to do, and it's actually more difficult to analyze that than to get this expression. But that's okay. We can. It's not too bad. So. So we need the range of VG for saturation, right? In order to do that, we're going to have to figure out, so we have two conditions for saturation, right? Back over here. VGS has to be greater than VT. Well, that one's easy. So we know VG has to be greater than, so we know VG then has to be greater than or equal to VT. So that one's easy. But the other one's a little tougher. We need to make sure that the VDS, the drain source voltage, is greater than VGS minus VT. In order to determine that, we need an expression for VDS, which we haven't developed yet. So we need to develop that. So we need the range of VG. The second condition for saturation gives that gives this in terms of VDS, the drain source voltage, which is, so we need to determine it. And how are we going to determine it? So from what? How are we going to decide what VDS is? KVL. Because we can write in terms of VS and VRL, right? So from KVL, we can say that VDS is equal to VS, the power source, minus VRL, the load voltage. Okay? We know what this load voltage is. We've already solved for it. So VS minus K over 2 VG minus VT squared RL. Okay. So the second condition for saturation, the difficult one to deal with, gives that VDS has to be greater than or equal to VGS minus VT. So if we rewrite that, we can plug in for VDS the expression that we just developed for VDS, right? So that's VS minus K over 2 VG minus VT squared RL. So that's VDS. It's greater than or equal to. The other side of the inequality is VGS, which we say is just VG, minus VT. Okay? So what we want to know is the range of VG, right? So this is the inequality that's going to give us the range of VG for saturation, right? All we have to do is solve this inequality for VG. Unfortunately, VG shows up on both sides of this, and it shows up quadratically. No fun. But this is another case of remember when you guys used things like quadratic formula to solve quadratic equations, which is fine, but with inequalities, which you guys like drew shaded regions in your solution space and all that of when the inequality was true. Yeah. Whew. And you were like, when is this going to be useful? Right now. Right now is when. So do that. I actually just punted and used Mathematica because I don't trust my algebra at 4 a.m. Quite frankly, I don't trust my algebra anytime, but 4 a.m. especially, it's bad. So I found that the range for VG is between VT minus, there's this sort of ugly fraction, 1 plus the square root of this kind of interesting constant 2K RL VS. That's an S. Not a very clear S. And this goes all the way to the end. Divided by KRL. And that is the lower bound of VG. And the upper bound of VG is a similar expression. It's VT plus a similar fraction minus 1 plus the square root. You can see the plus or minus emerging here from a quadratic equation. 2k RL VS divided by k RL. Whew. So this is our upper bound. The lower bound, though, remember there are two conditions. And the first lower bound was that VG had to be greater than VT, which is stricter than this bound, right? Because VT minus some positive number is less than VT. So we're going to replace this with VT less than or equal to the same stuff. That's the stricter bound. If you compute this with the numbers that were given, you get that VG has to be greater than, so 0.7 volts was given for VT, right? And it has to be less than or equal to, if you compute it, it came out to be a nice 5.33 volts. So I actually just totally made up the numbers in this problem, and they worked out to be like nice values, and I was like, sweet. Love it when that happens. It almost never happens, but it did work out. So, good. So that's the valid range for saturation, and so that means that's the valid range for this expression right here, right? For the voltage across the load, which is what we're trying to solve for. So now we know the range that we can plot this voltage across the load. So now we know the range for which we can actually move this voltage around and feel confident that our equations are predicting what's going to happen. Okay? And if you plot it, you get this pretty little blue curve here. And what this blue curve says is, oh, okay, if you change this gate source, or the signal source, from in your range, so from 0.7 up to, this is 5.33, up to there, the voltage across the load is going to go from approximately 0 up to approximately 5 volts. You might think, why didn't I just apply VG to RL, right? Like if you're going to put in from small voltage to 5 volts and you're going to get out from small voltage to 5 volts, why not just put it across the load? And why can we not do that? Why would that not work? What's the downfall of, so what happens if VG, because we could totally just hook VG right up to the load and just go ahead and do this. What's the limitation of our VG? Power. Right? So there's going to be current that's going to be drawn by this load, right? From VS. So there's going to be some current drawn, whereas VG experiences no current draw because it's just seeing this infinite impedance. So it's just changing however it wants, and it's easy to change. So this current, if we were to hook VG right up to this load, it would have to supply current. And what we're saying is oftentimes our variable sources can't supply the current. So that's why we can't just hook it right up. We use this MOSFET instead, and this bigger power supply that's not variable to actually supply that power. in a variable fashion. So that's what we've done. I've tried to come up with a good analogy for this. It's like something that's like small but versatile, and then something that's like big but not versatile, and then you put them together. Yeah.
Could you scroll to the bottom of the first image?
Sure. But
So
it's
only,
go ahead. Yeah.
only VT. So that first part is reduced down to VT, and is the second part still the?
Yeah. The second part is still all this. So this double quotes just means ditto. So
Okay.
this is still VG, and then we would just rewrite all of this down here. So that's the full expression. And I just plugged in numbers for VT. And the reason why this left-hand side I replaced with VT is that this expression is actually less restrictive than our other condition. Our other condition was that VG has to be greater than VT. Actually, it shouldn't be equal to, right? VT is supposed to be greater than VG for saturation. And
Is that the same for the non-condensed or the part right above it, where it's greater or less than or equal to?
right here,
Yeah, to the left, right there.
this guy. So what we're saying is this is what condition 2 requires. Condition 2, which we'll say this one right here is condition 2. And this one we'll call condition 1. So condition 1 is that VG has to be greater than VT. So this is condition 1. And they both have to be true. So condition 1 and condition 2 have to be true. Condition 2 have to be true. So condition 2 is true for this expression. Condition 1 is true for this expression. And if they both have to be true, that means that we're more restrictive, right? So there's a region of condition 2 for which condition 1 is not met. And so we have to restrict it. And there's also a condition in condition 2 for which condition 1 is not met. Sorry, I think I said that backwards. And so we're just taking we're taking the intersection of those two domains, if you want to think of it in terms of combinatorial logic, which nobody does. But yeah.
One is like sort of like a bubble of numbers, and then the other one is like half of all numbers.
Yeah, so if you think of this as being our VG number line, condition 1, so if this is our VT, condition 1 says you got to be in this region. Condition 2 says you got to be in this region. So our composite condition is the intersection of those two, this interval here. All right. Have a nice weekend.